All right, welcome to the deep dive. Today, we're taking a look at something really fascinating and, to be honest, sometimes a little bit unsettling when you really get into it. Deep reinforcement learning research.
Oh, yeah.
We talk about it all the time on the show, and it's clear that this area of AI is just exploding right now, powering all kinds of amazing breakthroughs from, increasingly sophisticated robots
Right.
to game-playing AI that can just dominate Go and Atari, which still blows my mind.
Yeah, it seems like every other week there's some new, big advancement being announced, and it's
Mhm.
really captivating to think about, like, all the potential applications out there. It's vast.
It really is. And that's actually what makes the research that you wanted to deep dive into today so important, I think. You brought this paper to my attention, and it asks such a fundamental question about all this progress we're seeing. Can we actually trust it?
Yeah, it's really about reproducibility.
Yeah.
And the paper's called Deep Reinforcement Learning That Matters. And it doesn't pull any punches.
Yeah.
It really gets into whether those amazing results that are being published, left and right, can actually be consistently replicated. And to me, that's such a crucial self-assessment for any field, but especially one that's moving this fast.
Absolutely, yeah. And we should mention this isn't just like a theoretical concern, right? The authors, they're from McGill and Microsoft Malupa, and they actually went and investigated how reproducible several of these like well-known model-free Paulus gradient algorithms really are. So we're talking about the core techniques here, the ones that are kind of the engines behind a lot of the really impressive RL systems we hear about: TRPO, DDPG, PPO, ACKTR, all the big names. Yeah.
Exactly. And they didn't just, stay in the theoretical realm. I mean, they actually
Yeah.
did a ton of experiments to really get at this question. And a lot of them use those classic Nujoko continuous control tasks from, OpenAI, Gym. So, environments like Hopper, which is always a fun one to visualize, right? Like trying to get this little it's basically like a pogo stick, trying to get it to balance and hop around.
Right, right.
And then half cheetah, which is, well, as the name suggests, is simulated half cheetah learning to run. And these environments, they're great for these kinds of experiments because they have such different characteristics.
Yeah.
Hopper, like you said, is super unstable, twitchy. Half cheetah tends to be a little bit more um, well behaved, I guess you could say.
Okay. So for everyone listening, our mission today is to understand why it's surprisingly hard to get the same results in deep RL research, even when you're using the same algorithms.
Right.
And we want to uncover, like, what are those factors that are contributing to these inconsistencies? Why is this such a big deal for AI as a whole? And then what are the steps that researchers can actually take to make sure that future progress is really built on a solid foundation, something that can be verified and built upon?
Yeah.
So I guess, like, let's just unpack this a little bit.
Yeah.
Why is reproducibility so important in the first place? Like, it's the cornerstone of good science, right? Especially in a field that's evolving as rapidly as deep RL.
It really is. I mean, in any scientific endeavor, reproducibility is absolutely fundamental. It's how we confirm discoveries, how we build upon previous work with confidence, and honestly, it's how we evaluate the significance of any new contribution.
Hmm.
If we can't reproduce findings, then it's almost like, you're trying to build a skyscraper on sand. You
Hmm.
you just can't be sure if what you're seeing is really progress,
Right.
Or maybe it's just a one-off event, or
Hmm.
or maybe it's due to some subtle differences in how the experiment was set up in the first place.
Right, right. It prevents the field from, going down these blind alleys and getting really excited about something that turns out to be, nothing.
I love that analogy, the skyscraper on sand. It's so true. And the paper actually points out that reproducing cutting-edge, deep RL results is seldom straightforward. And I
Yeah.
feel like that's kind of a polite way of saying it's a real pain a lot of the time.
It can be, yeah.
Yeah.
And they actually reference earlier work, a study back in 2017 by Islam and his colleagues, which had already, found this really surprisingly wide range of reported results for the exact same baseline algorithms.
Oh.
And that, right there, that's a red flag for the field, right? If we can't even consistently get the same outcomes with these established methods, then how can we be confident about any improvements claimed by new ones? Like, it calls everything into question a little bit. For sure, for sure. So let's try to break down what some of those main reasons behind this challenge are in deep RL specifically. And I know the paper kind of divides it into these two main categories, right? Things that we control in the experiment, and then things that are kind of more inherent to the whole process.
Yeah, yeah, exactly. So they look at these extrinsic factors, which are things like, um, the specific settings we choose for the algorithms, the hyperparameters,
Right.
and also just the actual software code that we use to implement them.
Mm.
And then you've got the intrinsic factors, which are more about like the inherent randomness of the whole learning process. So like how much do things like initial random settings matter? Those are called random seeds.
Right.
And then just the characteristics of the environment itself that the agent's learning in. Like those can play a huge role.
Yeah, absolutely. And just as a reminder, the focus here is really on policy gradient methods in continuous control. So these are the techniques where neural networks are learning to make decisions in these environments where the actions aren't just like discrete buttons you can press, but they're continuous values, right? Like
Yeah.
think about controlling the steering angle of a car
Right.
or the force applied by, a robot arm or something.
Exactly, yes. So things like TRPO, which you can think of it almost like a careful driver, making these small, safe adjustments to kind of stay on the road.
Hmm.
Then you have DDPG, which takes a more kind of direct approach. It tries to learn a specific action for each state, and it's guided by what's called a critic, which kind of evaluates how good those actions are.
Right.
Then there's PPO, which is kind of like a more efficient and maybe a little more user-friendly version of that careful driver analogy for TRPO. And then you've got ACKTR, which uses some pretty advanced math to kind of fine-tune those adjustments even further. So, yeah, these are all really powerful tools, but as we're going to see, they can be pretty sensitive too.
For sure, for sure. And to really put these algorithms to the test, the researchers used those Mujoko environments in OpenAI Gym that we talked about. So Hopper, half cheetah, but also there were a couple of others that presented their own unique challenges, right?
Yeah, definitely. So they also experimented with Swimmer, where the agent has to, learn to propel itself through water.
Yeah.
And there's Walker Tekken, which is a bit more complex. It's a simulated bipedal robot, so it's got to learn how to walk upright.
Mm.
And the idea really was to see how these algorithms performed in a variety of different environments, each with its own kind of dynamics and stability.
Right, right. So, okay, let's start digging into those extrinsic factors. And I think the first one that the paper really goes into is hyperparameters, right?
Yeah.
Like it seems like this is where a lot of the variability can just creep in and it can be really hard to track down. So just how sensitive are these algorithms to their settings?
Oh, they're tremendously sensitive. The right hyperparameters can be the difference between, an algorithm that learns super effectively and one that just completely fails or performs really poorly.
Mm-hmm.
And the problem is that what constitutes the quote-unquote optimal settings, it can vary a lot across different research papers, even when they're using the same algorithms and environment.
Yeah.
And often researchers don't even report the full range of settings that they experimented with.
Yeah.
So, it's really hard to know if what they found is truly a breakthrough or just a lucky combination of hypoparameters. And that can lead to some pretty unfair comparisons.
Yeah, it makes it incredibly difficult for anyone who's trying to actually build on that work, right? It's like trying to recreate a complex chemical reaction.
Exactly.
But you don't know the precise temperature or you don't know the exact amounts of each ingredient.
Yeah. It's like a recipe that's missing some key details.
Yeah.
And that lack of transparency and just consistency across the field, it can lead to situations where, someone's showcasing their new algorithm and they're comparing it against a baseline. But that baseline hasn't really been tuned to its optimal settings. And so they might mistakenly conclude that their method is like way better when in reality it might not be.
Right. Right. So the paper kind of zooms in on specific hyperparameters. And the first one I look at is network architecture, which makes sense, right? Given that we're talking about algorithms that are built on neural networks.
Right.
So what did they discover about the impact of, just the design of the network itself? Well, what they found, and this is consistent with some earlier research as well, is that the choice of network architecture, and by that I mean both its structure, so like the number of layers, the number of neurons in each layer, and then also the activation functions that are used within those neurons, these choices can have a huge effect on performance.
Wow.
And that's true for both the policy network, which is the one that's actually deciding what actions the agent should take.
Right.
And then the value function network, which is kind of estimating the potential future rewards for different actions.
Okay.
And the takeaway here for anyone listening is that even these seemingly minor choices in network design can actually be the real driver of some of those reported performance gains that we see in the literature.
That's interesting. And they tested a few different what are called multi-layer perceptron architectures, or MLPs, right?
Mm-hmm.
Yeah. So they experimented with, configurations like 64-64, which is basically two layers with 64 neurons each.
Yeah.
150, 25, that's a three-layer network.
Yeah.
And the number of neurons kind of decreases as you go deeper.
Right.
And then a larger one, 400, 300, which had, significantly more neurons. And these are all architectures that have shown up in different research papers.
Okay.
And then, in addition to the architecture itself, they also looked at different activation functions, things like TON, ReLU, and leaky ReLU.
Mm-hmm.
And they applied those to both the policy and the value networks. And then, just to make things even more interesting, for the ACKTR algorithm's value function, they also used what's called an ELU activation.
So they were really trying to cover their bases,
Yeah.
explore all the different options that are out there.
Exactly, yeah. And what they found, and you can actually see this really clearly in Figure 2 in the paper, is that algorithms like PPO, TRPO, and TDPG, they're really sensitive to these architectural choices.
Mm.
And they observed that, while using ReLU or leaky ReLU often led to the best performance, that wasn't always the case. And the effects were kind of inconsistent across different algorithms, and even like the same algorithm in different environments. So it wasn't like there was one magic bullet activation function that always worked the best.
Mm. So what works well for PPO might not be the optimal choice for DDPG, even if they're both trying to, get that cheetah robot to run as fast as possible.
Exactly, yeah. And that really highlights that the network architecture isn't just this isolated choice, right? It's all intertwined with how the algorithm itself works, like the underlying mechanics of it. And the authors even suggested that if you're using a larger network like that 400, 300 one, you might need to adjust other hyperparameters as well. So things like the clipping parameter in PPO or the learning rate to keep things stable. So it's like this really complex ecosystem where changing one element can have all these ripple effects throughout the whole system. And that just goes to show why getting reproducible results is so challenging.
Yeah, absolutely. And it leads to this really interesting idea that they bring up, this idea of hyperparameter agnostic algorithms.
Right.
Which sounds amazing, like methods that can just kind of figure out their own settings during training, at least to some extent, so that we don't have to do all this manual tuning. And that could potentially make comparisons across different studies much more meaningful.
Yeah, it's almost like the holy grail, right? To have algorithms that are just, less sensitive to these really fine-grained settings.
Exactly, yeah. Okay, so another key hyperparameter that they investigated was reward scale. And I think, for people who aren't super familiar with RL, this might not seem like a big deal, but it turns out it can have a really big impact.
It can, yeah. And so reward scaling is basically where you just multiply all the rewards that the agent gets from the environment by some constant number.
Okay.
And researchers have been doing this for a while, especially with algorithms like DDPG, to try to improve the learning process.
So why does that actually help?
Well, the idea is that in a lot of these deep RL algorithms, they're using what are called gradient-based methods. So they're relying on these gradients, which are essentially like, directions for how to adjust the neural network weights. And if the reward signals are really large or really sparse, it can mess with those gradients and cause problems.
Okay.
So think about it like, you're trying to train a dog. If you're like overly enthusiastic and you're giving the dog a huge reward for every tiny little thing they do,
Right.
it might not be that effective. Or on the other hand, if you only give them these infrequent, like giant rewards, that might not work very well either. So reward scaling is kind of like trying to find that sweet spot, make those reward signals a little more manageable for the learning process.
So it's about making the feedback signal more, like, I guess, digestible for the algorithm to really learn from.
Exactly, yeah. And there's this common rescaling factor of 0.1 that you see in a lot of papers, which basically means you're just dividing all the rewards by 10. But what the authors found, and you can see this in Figure 3, is that the impact of reward scaling is actually way more complicated than that.
Yeah.
They tested DDPG on half cheetah, both with and without something called layer normalization, which is a technique that can kind of help stabilize the internal activations of neural networks.
Mm.
And what they found was that the results were really inconsistent depending on the scaling factor they used. And sometimes if they used a very small scaling factor, the algorithm just wouldn't learn anything at all.
Oh.
So the presence or absence of layer normalization, it just made the whole thing even more complex.
Yeah. So it's not as simple as just, picking a scaling factor and going with it. It seems like there's this interaction going on with other aspects of the network itself.
There is, yeah. And it suggests that, that effect of reward scaling, it really is tied to those complexities of deep networks
Yeah.
and how we're using gradients to optimize them. And the authors actually point out that we might need a more principled approach to handling rewards altogether.
Interesting. So what would that look like?
Well, they reference some research that's looking into more dynamic and adaptive ways of managing reward signals.
Hmm.
So instead of just, multiplying everything by a fixed number, you might adjust the scaling factor over time.
Okay.
You might use different scaling factors for different parts of the reward signal. So yeah, it's all about moving away from that blunt instrument and thinking more carefully about how the reward structure itself is shaping the whole learning process.
Yeah.
And they even highlight that some benchmark environments might just have like inherently poorly tuned reward scales to begin with,
Right, right.
which could unfairly disadvantage certain algorithms in those settings.
Right. Yeah, that makes sense. Okay, so let's shift gears a little bit and talk about those intrinsic factors now, the things that are kind of built into the whole deep RL process. And the first one that the paper looks at is the role of random seeds and the number of experimental trials that you actually run.
Yeah.
And I mean, this seems like such a fundamental part of any kind of scientific investigation, right? Like you always want to make sure that you're running enough experiments to be confident in your results. But in deep RL, it seems like that's even more important because of all the randomness that's involved.
Absolutely, yeah. And that randomness comes from several sources. So
Yeah.
the environment itself might have some inherent stochasticity to it.
Right.
Things might not always behave exactly the same way every time you run it.
Yeah.
And then the learning process itself is definitely stochastic. So for example, those initial weights of the neural network, they're set randomly, which means that if you run the exact same algorithm with the exact same hyperparameters, but you just change the random seed, which is like the starting point for that random number generator,
Right.
you can end up with very different outcomes.
Yeah, and figure 5 in the paper, it really drives that point home. They show TRPO running on half cheetah with identical settings,
Right.
but different sets of random seeds. And the learning curves they're just dramatically different. It's really striking.
It is, yeah. And that just underscores this practice that you see sometimes in published work where people will just select the best performing trials, or they'll average over a really small number of runs, like maybe less than 5. And that's just, it's super misleading. It's like, showing only your best golf swing and ignoring all the ones where you shank the ball into the woods.
Yeah, you're not getting a true picture of how well the algorithm performs typically.
Yeah.
Exactly, yeah. And so while the paper doesn't say, like, here's the magic number of trials that you need to run, they definitely emphasize that the amount of variability that they saw suggests that, averaging over just a few runs or picking the best one, it's just not a good practice.
Right. So more trials is always better, basically.
It seems that way. And they even suggest that we might want to look to methods like power analysis, which statisticians use to determine the necessary sample size, to detect a real effect.
Right.
And those methods might offer some guidance here.
So, it's all about getting a more reliable picture of the algorithm's average performance and its consistency.
Exactly.
Okay, so the next intrinsic factor they look at is the properties of the environment itself. And I think we've kind of touched on this already a little bit.
We have.
With the hopper versus half cheetah, but it turns out this is actually a really big deal for reproducibility too.
It is, yeah. The choice of the environment that you use to evaluate an algorithm, it's super critical. And as we've been talking about, continuous control environments, they can have vastly different characteristics. Some might have randomness built into their physics.
Right.
Some might naturally have really short episode lengths. The overall stability can vary a lot. And you can see this really clearly in Figure 4 in the paper, where they show how these different policy gradient algorithms perform across a bunch of different MuJoCo environments.
Yeah.
And what's interesting is that there's no single algorithm that emerges as like the undisputed winner across all of them.
Right.
So, for example, DDPG, it tends to do pretty well on half cheetah, which is that more stable environment, but then its performance just tanks on hopper, which is much more unstable.
Okay.
And the authors, they suggest that this might be because DDPG has this inherent exploration noise. It kind of tries out random actions to see what works best.
Right.
And in an unstable environment, that can lead to a lot of failures. And those failures tend to lead to these really short training episodes,
Right.
which can cause the algorithm to get stuck in this suboptimal strategy where it's just trying to survive, basically.
Yeah.
And then there's this other interesting example with the swimmer environment where TRPO seems to be the top performer, but even that result comes with a big caveat.
So what's going on there?
Well, they pointed out that in the swimmer environment, it's actually possible to learn a policy where the swimmer basically just curls up into a ball and flails its limbs around.
Uh.
And that can actually get you pretty decent rewards, even though it's not really swimming effectively.
Hmm.
So it's like it's found this way to game the system, without actually solving the task in the way that it was intended.
Right, right.
And that really emphasizes that we can't just rely on reward numbers alone. We need to actually look at the behaviors that the algorithms are learning to make sure that they're actually solving the task in a meaningful way.
Yeah, so we need to be really careful about the environments that we use to test these algorithms and report results. And it seems like presenting results on a variety of different environments is essential to get a good understanding of the algorithm's capabilities and also its limitations.
It is, yeah. Because if you just showcase your results on, the environments where your method happens to excel,
Yeah.
it can create a very misleading impression of how good it is overall.
For sure, for sure. Okay, so we've talked about hyperparameters and environment factors. There's another big piece of the puzzle here, and that's the code base itself. So, in theory, different implementations of the same algorithm, they should give you comparable results, right?
You would think so, yeah.
But the paper actually found that that's not always the case.
Yeah, it's kind of surprising, but even though the algorithms might be, described in the same way, the actual implementations can vary a lot, and those variations can have a big impact on the results you get.
Hmm. So what are some of those variations that they found?
Well, researchers will often implement their own versions of these baseline algorithms.
Right.
And those implementations, they might contain subtle differences that, maybe aren't always clearly documented in the publications.
Right, right.
So things like, what specific optimization algorithm are they using for a particular subcomponent? Or even small differences in, like, the control flow of the code. Those can add up. And to really investigate this, the researchers actually compared different implementations of TRPO and DDPG that are, publicly available. So for TRPO, they looked at implementations in OpenAI baselines, the original TRPO code base, and then RLab. And for DDPG, they compared RLab Theano, RLab++, and then OpenAI baselines again.
So they were really, comparing apples to apples here, making sure that
Means that-
it's the same algorithm just implemented in different ways.
Yeah, exactly.
And what did they find?
Well, after training these different implementations for the same number of steps, which was 2 million samples, they found that the final performance could vary a lot. And that's shown pretty dramatically in tables 1 and 2, and also in figure 6 in the paper.
Yeah.
So yeah, it's clear that even for these well-established algorithms, the specific details of the implementation, they can really matter.
So what's the takeaway message here for researchers?
Well, I think the big thing is transparency, right? If you're comparing your new method against a baseline algorithm, you need to be super clear about which implementation you're using.
Right.
And ideally, you would even show that your baseline implementation matches the performance that was originally reported for that code base.
Yeah.
Just to make sure that everything's consistent.
Yeah, that makes sense. Okay, so we've covered a lot of the factors that make reproducibility tricky in DeepRL. Let's talk about, how we actually evaluate these algorithms in the first place, how we report their performance. And the paper kind of touches on this idea that it's common practice to just report the average cumulative reward, or maybe the highest reward achieved. What's wrong with that? Why isn't that enough?
Well, the problem is that, as we've been discussing, these algorithms, they can be pretty unstable. Their performance can jump around a lot from one training run to the next. So just reporting an average or a maximum value, it doesn't really tell you anything about that variability.
Right.
It doesn't give you the full picture. You might have a really high average that's driven by a couple of, really lucky runs, but then the majority of the time, the algorithm's actually performing poorly.
Right.
And you're not going to see that if you just look at the average.
So we need a better way to understand the typical performance and the range of possible results.
We do, yeah.
Yeah.
And that's where confidence intervals come in, which the paper talks about quite a bit.
Okay, so can you explain, in simple terms, what a confidence interval is and why it's so much more informative?
Sure. So a confidence interval, it basically gives you a range of values where the true performance of the algorithm is likely to fall. And it's usually associated with a certain probability, like 95%. So, you're 95% confident that the algorithm's true performance is somewhere within that range.
Right.
And that gives you a much better sense of, you know, how consistent and how reliable the algorithm is. If the confidence intervals are really wide, it's like, okay, there's a lot of variability here, and that average might not be very representative.
Right, right. So it's not just about like the single point estimate. It's about understanding the spread, the range of potential outcomes.
Exactly.
Okay. And the paper also makes this distinction between evaluating an algorithm during the learning process, which they call the online learning view,
Right.
and then evaluating the final learned behavior, which is the policy optimization view. So which one of those is more relevant when we're talking about reproducibility?
Well, both perspectives are important, but the paper mainly focuses on that policy optimization view.
Hmm.
So that's where you train the algorithm, and then you evaluate the quality of the final policy that it's learned, by running it for a bunch of episodes. And that's usually how we assess the ultimate performance that an algorithm has achieved.
Okay. And to actually calculate those confidence intervals, the researchers used this statistical technique called bootstrapping. Can you give us like a simple explanation of how that works in this context?
Sure. So imagine you have a limited number of experimental runs. Right. You've run your algorithm a certain number of times. Bootstrapping is basically where you repeatedly resample from those results that you've already got. But you do it with replacement, which means you can pick the same result multiple times.
Okay.
And you use that to create many, many simulated data sets. And by analyzing the distribution of outcomes across all of those simulated data sets, you can get a better estimate of the true underlying performance distribution. And then from that, you can calculate things like the mean performance and those crucial confidence intervals.
Okay. Okay. And so table 3 in the paper actually gives some examples of these bootstrap confidence bounds. And you can see that there's quite a bit of variation, right, across different algorithms and different environments.
There is, yeah. And interestingly, TRPO and PPO, they tended to show tighter confidence bounds, which suggests that they're maybe a bit more stable, at least in the settings that they tested.
That's interesting. And I think, as you mentioned earlier, if those confidence bounds are wide, it's basically a sign that you probably need to run more experiments to get a more reliable estimate, right?
Yeah, absolutely. More data is almost always better when it comes to these kinds of things. And to figure out if you've run enough trials, the paper also talks about this thing called bootstrap power analysis, which is a way to estimate whether your current number of experiments is actually enough to detect a meaningful difference in performance if one truly exists.
So how does that work?
Basically, you take your existing data and you simulate a scenario where there's a small but real improvement in performance. So in the paper, they used a uniform increase of 25%.
Okay.
And then, using that bootstrapping technique that we
Yeah.
just talked about, you can see how often you would correctly identify that improvement as being statistically significant.
Okay.
And if you find that you're only detecting it a small percentage of the time, it suggests that your sample size just isn't big enough. You need to run more trials to have enough what they call power to detect real differences. And their analysis showed that in those more unstable environments, more trials were definitely needed.